Hello. I'm here today to try and explain time dilation as it's in the sense of perpendicular to the velocity of motion to a layman. So with that being said, I'd like to start by saying that in general, special relativity is very hard to conceptualize, and so just please, throughout this video, be patient with yourself, try and combat any kind of disappointment with yourself with the fact that this is difficult. So please be kind to yourself. You can understand this, I promise you, if you just give yourself the time to do that. Okay. So, let's start by explaining the definition of velocity when it's constant is the change in distance over change in time. Now, it must be said that this is only for a constant velocity. If something is accelerating, meaning the velocity is changing, then this is not the accurate definition. There are things you need to add that zero out when it's constant, and therefore you're left with this. Okay, so in special relativity, you only deal with constant velocities because accelerating objects have a force on them, and therefore the laws of physics are not necessarily the same for every reference frame. Okay. Okay, so let's get started. So here's the definition of a constant velocity. Now, if we were to represent this in an arrow, or as it's called, a vector, we would point it in the direction of the change in distance. So this velocity is moving to the right, so change in distance is to the right, and that's the direction we're pointing to. Okay, so imagine a train moving with a constant velocity to the right, and we've got a basic clock, which is just a light that gets emitted, moves a distance up, hits a reflector, then moves the same distance down. So it ended up traveling 2D. Okay. In the vertical sense, an observer on Earth is going to see this as moving triangularly, because as it's moving up to this observer, it's also moving to the right, and if you represent that, it will be moving diagonally. Okay, I think now is an important time to note that this velocity is a velocity between the reference frames. The observer on Earth sees this as moving to the right with this velocity, but someone observing on this spaceship will see the Earth moving to the left with the same velocity. So it is the velocity between them and not the velocity of the spaceship itself. But in this guy's perspective, that is what it is. Okay, it is the velocity of the spaceship moving to the right. So we're gonna go off that basis, kind of. So let's go back to this triangle. Okay, now a postulate in the special relativity is that the speed of light is constant, so it equals c in every reference frame. It doesn't matter if you're walking, if you're on a train, blah blah blah, it's still c. So instead of, for example, if you're moving in a car on Earth, someone on the ground is going to see you moving at 25 miles an hour. Now, if there's also a train and someone on the ground sees it moving 100 miles an hour, you will only see the train moving at 75 miles an hour because you would add or subtract the velocities in order to obtain your perspective of their velocity. Okay, so in vector form, we've got c moving diagonally in this, as this guy observes. It's moving at a constant velocity in the diagonal direction. Now, the horizontal direction is the velocity of the spaceship itself. So the horizontal component of the speed of light in this guy's reference frame is v. And because v is a ratio, you don't half it when you half the triangle, or the horizontal component of the triangle in this scenario. Okay, now we can use the Pythagorean theorem in order to obtain the vertical component of the speed of light in this guy's reference frame. So that's going to end up being the square root of c squared minus v squared. Okay, so that's the vertical component. Now, I think it's vital to explain that we can only truly compare the vertical components because in the spaceship's reference frame, the vertical component is the entirety of the event. And we cannot compare something that doesn't exist for both reference frames. So we're comparing the only thing that truly exists for both reference frames. Okay, so that's a difficult concept to kind of grasp, especially if you're presented with it just now. So just please be kind to yourself. Yeah. Okay, so we've got the vertical component in the Earth guy's reference frame here. Now this is the vertical speed. So we're going to equate this to the definition of speed, and we're gonna say it's equal to 2d over change in time. Right. So the 2d, it went up and down. It went up down twice, and in a certain amount of time from Earth's reference frame. Okay, now let's look at the velocity on this in the spaceship's reference frame. That's going to be c, the constant speed of light, is equal to 2d again over change in time, but instead of, because these times are not equal, and we're going to prove that in a second, we're going to call this change in tau, which is called the proper time. Yeah. So let's work with this. Let's see how we can directly compare these two. Okay, so let's start with this one. We've got, okay, let's move over here. We've got 2d over change in t equal to square root c squared minus v squared. Let's solve for t. So we're going to bring that over here. We're going to bring this down. It's going to end up being 2d over the square root of c squared minus v squared equal to change in time. Let's do it that way. Now let's pull out a c here, a c squared here, under the square root, which becomes a c if you take it out. So this, let's move this way. We've got 2d over c over the square root of 1 minus v squared over c squared. So I hope you see what I did there and how that works. Okay, so we've got 2d over c here equals the change in time in this guy's reference frame. And then we've got c equals to 2d over change in tau in the spaceship's reference frame. So let's solve for change in tau over here. So this is going to be equivalent to change in tau is equal to, guess what? 2d over c. Now, so we can input this here, and we can directly compare the change in time in these two reference frames. Okay, and so the change in time on the Earth's reference frame, or the stationary reference frame to the observer, is equal to change in tau over the square root of 1 minus v over c squared. This is time dilation with perpendicular motion. So yeah, that's pretty amazing. And I think right now it's important to note that change in time is not a vector like velocity or change in distance. So you can't really take, I mean, obviously you can take components of time, you know, but the time itself is, I don't want to say static or constant for a reference frame, but basically, yeah. Okay, well, that's my video. So I hope I, you know, stimulated your curiosity. I hope you're satisfied, you know, with this. And like, there's tons of other material that you can search in order, if this didn't, you know, really sink in for you, that you can find online. You know, just please, you know, try to combat any discouragement in your own self-worth, because understanding exists and you're capable of obtaining it. So peace.